The requirement originated inside a small Admiralty directorate. Its name was the Directorate of Miscellaneous Weapons Development. The tasking directive described a defined concrete problem. German coastal defences formed the so-called Atlantic Wall barrier. Sections of that barrier used thick reinforced concrete. Measured wall heights approached 3 meters in many sectors. Thicknesses around 2 meters were reported in staff summaries. Staff analysis concluded handheld charges were inadequate. Required explosive mass exceeded 1 long-ton equivalent. Standard engineer stores could not deliver that mass safely. The Directorate therefore considered remote delivery methods. Conventional vehicles were evaluated and rejected for exposure. Tanks carrying large demolition charges risked crew loss. The guided boats required precise steering under heavy fire. Air-dropped bombs lacked accuracy against vertical seawalls. A surface-running unmanned device was judged preferable. The selected concept was geometrically simple and unusual. 2 large wheels contained the propulsion and structure. Between them sat a cylindrical explosive drum. Propulsion would come from cordite rockets fixed radially. The assembly received the designation Panjandrum internally. Informally, it became known as the Great Panjandrum. The wheels defined the overall dimensions of the machine. Each wheel measured approximately 10 feet in diameter. Tread width was around 1 foot per wheel. Timber segments formed the main wheel discs. Steel tires and cleats were bolted around the circumference. Cross-brace spokes provided stiffness against torsional loads. The central hubs carried bearings around the explosive drum. The drum length has been cited near 6 feet. Its diameter allowed packing of roughly 1 ton explosive. Cordite rockets attached to the outer wheel faces. Brackets held each rocket parallel to the tangent. Exhaust jets acted along the wheel circumference tangentially. Combined thrust produced forward rotation of both wheels. Design estimates predicted speeds near 60 miles hourly. At that speed, kinetic and explosive energy combined. The intent was to punch a tank-sized breach. Operationally, the device would launch from a landing craft. The craft would approach to shallow water offshore. Rockets would ignite while the wheels were partially submerged. The machine would roll down a ramp into surf, then traverse the foreshore under rocket propulsion alone. Her impact with the wall would trigger the explosive filling. The design challenge lay in stability and trajectory control. The Directorate required at least approximate directional reliability. Deviation outside an acceptable cone implied mission failure. The structure also had to withstand uneven beach surfaces. Rockets had to survive ignition loads without detaching. Initial fabrication occurred in an industrial area, Leytonstone. Workshops assembled wheels from machined timber segments. Steel strips were rolled and punched for treads. Welders prepared brackets for multiple rocket units. The central drum remained inert during early construction. Sand or ballast substituted for high explosive during development. Once assembled, the prototype required discreet transportation. Police escorted convoys at night along predetermined routes. The canvas covers reduced visual recognition from casual observers. Destination was a test beach near Westward Ho. The area already hosted amphibious training infrastructure. Despite security arrangements, the location attracted holiday visitors. Trials therefore occurred under mixed military and civilian observation. Test schedules aligned with tide tables and training availability. Safety cordons were marked with flags and sentries. Detonation risks were limited using sand-filled drums initially. The first known trial used a reduced rocket count. Ignition lag between units produced uneven initial torque. The machine left the landing craft as planned. It gained speed across wet sand in a straight line. Then rockets on one wheel underperformed or extinguished prematurely. Asymmetric thrust caused yaw and path curvature rightward. Her observers recorded a deviation away from the notional target. The device eventually toppled or coasted to rest harmlessly. Subsequent tests incrementally increased rocket numbers each side. Engineers altered clamp designs to secure rocket casings. They assessed different ignition harnesses for synchronous firing. Electrical systems were considered, but primarily used fusing cord. Ignition typically progressed from rearward to forward rockets sequentially. This profile attempted to maintain thrust as earlier units burned. More thrust magnified every small asymmetry in performance. Minor differences in rocket impulse produced large yaw moments. Wheel flex under load introduced further random steering effects. Soft sand patches produced differential rolling resistance between wheels. An impact with small craters deflected the trajectory unpredictably. At one stage, designers added a stabilizing third wheel. This wheel mounted behind the drum on a frame. Its purpose was to reduce lateral oscillation and pitching. It also increased ground contact points for overall stability. With the third wheel fitted, rocket numbers again increased. The device achieved higher speeds during these specific trials. However, dynamic behavior remained sensitive to small disturbances. Reports describe rockets detaching from mounts during acceleration phases. Clamp failures allowed burning units to separate and tumble. Detached rockets followed erratic paths around the test area. Some traveled over observer positions or into the shallows. Risk assessments flagged unacceptable hazard levels around the weapon. The third wheel also complicated steering intentions. It altered load distribution across the primary wheels. Contact conditions changed whenever the beach profile varied. On uneven ground, the third wheel sometimes carried excessive load. This altered friction on the main wheels unpredictably. After reviews, engineers removed the third wheel again. Attention shifted to steering via external control inputs. One concept used steel cables attached to wheel rims. Personnel on the flanks handled these cables during tests. By tensioning one side, they sought to correct deviations. The method assumed manageable loads along the cable length. In practice, cable loads exceeded prior assumptions significantly. Under high thrust, cables tightened and then snapped. Recoiling lengths of steel cable whipped back across sand. These failures added another source of uncontrolled hazard. Steering effectiveness remained unreliable even when cables held. Engineers also investigated thrust trimming using differential rocket counts. They attempted to offset known wheel imbalances systematically. Some configurations staggered rocket ignition timing between sides. Others adjusted radial placement to influence torque characteristics. These incremental modifications produced only limited directional improvements. Throughout testing, the drum generally contained sand filling. This choice minimized consequences of full structural failures. However, sand shifted internally during aggressive maneuvers. Shifting ballast altered the center of mass mid-run. This generated additional pitching and rolling instabilities. And instrumented measurements were rudimentary by modern standards. Observers relied heavily on visual tracking and stopwatch timing. Photographic sequences provided some frame-by-frame motion analysis. Footage from naval photographers captured several key trial runs. Nevertheless, precise quantification of forces remained limited. Minutes from internal meetings emphasized schedule pressures strongly. Staff understood looming assault operations against occupied Europe. There was interest in availability before those operations commenced. That timetable constrained redesign cycles and deeper analytical studies. Alternative breaching methods existed in parallel development streams. Engineer tanks used demolition guns against pillboxes and obstacles. Bangalore torpedoes offered trench and wire clearance capabilities. So large naval bombardments could damage selected fortifications pre-landing. The Panjandrum competed for resources within that environment. Eventually, requirements were relaxed regarding directional precision. Correspondence indicated it need only travel generally forward. This administrative change reflected difficulty achieving fine control. Even under eased criteria, test runs remained inconsistent. Many runs deviated markedly from the intended corridor. A final major demonstration was scheduled for senior observers. Attendees included naval officers, scientists, and official photographers. Safety perimeters were marked, though within existing beach constraints. The drum again contained sand rather than live explosive. Rocket complements were near the maximum practical number. Initial ignition appeared uniform across both wheel faces. As the machine rolled from the landing craft into shallow water, it transitioned from surf onto firm beach without incident initially. Speed built rapidly as more rockets reached full thrust. Wheel rotation rates increased to visually striking levels, then one rocket clamp reportedly failed under load. A burning rocket separated and altered thrust distribution suddenly. Additional clamps yielded, causing successive rocket detachments. A symmetric thrust produced oscillatory yaw across the beach. The device encountered a line of shallow test craters. Contact with those depressions amplified steering irregularities sharply. Witness accounts described the machine turning off its planned axis. Its path brought it closer to assembled personnel areas. Detached rockets continued traveling independently across the sand. Observers moved quickly behind available cover along the ridge. Cameramen and officers repositioned to avoid potential impact lines. Shortly afterwards, the device lost remaining coherence entirely. Structural elements separated and individual components disintegrated. Residual propellant charges detonated or burned out on the surface. Cordite units produced localized secondary explosions on the foreshore. When motion ceased, debris lay scattered over a wide area. No live explosive had been present in the central drum. Consequently, damage was limited to hardware and beach surface. However, risk to nearby personnel had been clearly demonstrated. Safety officers considered casualty probabilities under operational loading. Their assessments indicated unacceptable exposure during real deployments, and the Directorate now reviewed cumulative test data and incidents. Tables summarized run distances, deviations, and failure occurrences. Statistical consistency requirements were compared to operational expectations. The Panjandrum did not meet thresholds for predictable performance. Mechanical robustness under maximal thrust remained unproven and doubtful. Engineering staff examined potential deep redesign options afterwards. Suggestions included completely revised wheel structures and suspension systems. Other ideas involved gimbaled rocket mounts or clustered nozzles. Some proposed gyro-based stabilization inside the central drum. Each proposal implied new prototypes and further prolonged testing. Against those costs, planners considered available calendar time remaining. And major amphibious operations were already in advanced preparation stages. Landing craft allocations were tightly scheduled across multiple formations. Any additional complex equipment would require training and integration. Documentation noted increasing reluctance to introduce unproven systems. Parallel deception operations were also underway within Allied planning. Some later commentary suggested the project served deception roles. It has been linked by historians to Operation Fortitude discussions. However, surviving technical paperwork reflects genuine engineering intent. The available evidence indicates sincere attempts at functional development. Ultimately, the weapon was not authorized for operational deployment. Project termination followed shortly after the final large demonstration. Remaining components were scrapped or repurposed for other uses. The concept did not feature during the Normandy landings assaults. Breaching duties fell to more conventional engineering systems instead. Post-war, the Panjandrum has occasionally been reconstructed experimentally. One replica used fireworks to simulate the original rockets. That device reportedly travelled only a short straight distance. Other demonstrations employed powered wheels and lightweight structures. These activities function mainly as educational or commemorative exercises. Within engineering literature, the Panjandrum provides a case reference. It illustrates constraints of unguided rocket propulsion on rough terrain. It highlights amplification of small asymmetries at high rotational speed, and it demonstrates difficulties steering multi-rocket arrangements without feedback. It also documents interactions between urgency and developmental thoroughness. Procedurally, the project generated a substantial paper trail. Memos requested extensions, additional trials, and modified safety controls. Procurement forms covered timber orders, steel tires, and rocket units. Transport schedules recorded night convoys and escort arrangements. Test logs documented weather conditions and tidal states each run. Failure reports itemized clamp fractures and rocket detachment instances. They noted cable failures, recoil paths, and near-miss coordinates. Recommendations followed regarding exclusion distances and observer placement. Cumulative documentation formed the basis for final cancellation recommendations. Within that framework, the Panjandrum remained an experimental object. It never progressed into standardized production or field issue. No manuals for combat deployment were ever distributed to units. Training establishments did not integrate it into formal syllabi. The machine's physical principles were straightforward in abstraction. Implementation on an actual beach introduced unmodeled complexities. Cordite rockets lacked uniform thrust under field conditions. Mechanical tolerances in wooden wheels permitted dynamic deformation. Surface irregularities produced unpredictable combinations of forces and torques. The Directorate continued other projects after this cancellation decision. Resources shifted towards systems showing you better reliability indicators. Some of those devices reached service and operational use, and others remained prototypes and left similarly limited records. The Panjandrum persists mainly through photographs and written descriptions. Images show the double wheels resting on the Devon sand. Another frame shows it lying on its side post-trial. Together, these records document an ambitious yet unfielded mechanism. Within archival context, the weapon occupies a narrow category. It represents high-risk rapid prototyping under wartime constraints. Its engineering narrative is bounded by repeated instability findings. Administrative records show firm termination once risk outweighed benefit. The device remained an experimental demonstration, not an operational tool.